ever just stare at a soap bubble and wonder where those wild, swirling colors come from? I mean, they're not really in the soap, right? Or maybe you've seen that same rainbow sheen on an oil slick after it rains. It looks totally magical, and today we're going to pull back the curtain and look at the physics that literally paints with light.
So what is going on here? How does a totally clear film of soap or a thin layer of oil create this incredible light show? The answer isn't a pigment, it's not a dye, it's this really cool dance that light performs on a scale so small you can't even see it.
Okay, let's get right into it. The name for this whole thing is thin film interference. And yeah, the name pretty much says it all. It happens when light interacts with a layer of something that is ridiculously thin. We're talking layers that are often just a few wavelengths of light thick.
And the best part is, you don't need some fancy science lab to see this in action. Nope, it's happening right there in the soap film on a kid's bubble wand, or in those shimmering patterns of oil on a puddle in a parking lot. These everyday things, they're going to be our labs for this explainer.
Now, to really get this, the first thing we have to remember is that light acts like a wave. And here's the crucial part. When you look at a thin film, you're not just seeing one reflection. You're actually seeing two different reflections, all mashed together. So let's trace the journey. First, a light wave comes in and hits the top of the film, like the outside of a soap bubble. Right away, some of that wave bounces off. We'll call that reflection 1. But the rest of the light, it keeps going. It punches right through the soap until it hits the bottom surface, the inside of the bubble. And there, it reflects again. That's a reflection 2.
And right here, this is where the magic happens. Those two separate waves, the one from the top and the one that took the scenic route through the bottom, they both travel back to your eye, and they meet up. The way they combine, or interfere with each other, is what creates every single color that you see.
But for them to interfere in just the right way to make color, we need to talk about a secret ingredient. It's a little concept from physics called a phase shift. And honestly, it is the key that unlocks this entire puzzle. So, what is this phase shift? Well, imagine a light wave is just a simple up and down squiggly line. A 180-degree phase shift is like taking that wave and just flipping it perfectly upside down. So the peaks become troughs and the troughs become peaks. This little detail, it's the reason for everything that's about to happen.
Now here's what's so wild. This flip doesn't always happen. It all depends on the surface the light hits. So when light traveling through the air hits the soap film, it's hitting something denser. Think of it like a hard reflection. The wave hits it and it flips 180 degrees. But when that light is inside the soap and hits the air on the other side, well, now it's hitting something less dense. We call that a soft reflection, and the wave bounces back with no flip at all. This one tiny difference, one wave flips, the other doesn't, is everything.
Okay, so with that secret phase shift in our back pocket, we can finally connect the dots and see how the thickness of the film is actually what's creating the color. When our two reflected waves meet up, one of two things happens. If their peaks and troughs line up perfectly, we say they're in phase. They add together and make a much brighter, more intense wave. That's constructive interference. But if the peak of one wave meets the trough of the other, they're out of phase, and they totally cancel each other out. Poof. Darkness. And that's destructive interference. So let's put it all together. Think about the very, very top of a soap film. You know, where gravity has pulled all the soap down and it's super thin. Wave 1 hits that top surface, and because it's a hard reflection, it flips 180 degrees. Wave 2 goes through the film, but since it's so thin, it travels almost zero extra distance. So when it comes back out, it's perfectly out of sync with the flipped wave 1. They cancel each other out. And that's why the very thinnest part of a soap film looks dark or clear. But a bubble isn't all one thickness, right? It's thicker at the bottom. So what happens when we get to a spot that's exactly 1/4 of a light wavelength thick? Well, this is where the color shows up. And this is how color is born. At this exact thickness, wave 2 has to travel down and back. That's an extra path of half a wavelength. That little delay is exactly what's needed to get it back in sync with a flipped wave 1. The two waves come out perfectly in phase, they reinforce each other, and bam, suddenly you see a bright, vibrant color. Okay, So you can probably see the pattern now. What happens if we go to a spot that's even thicker, say half a wavelength thick?
Yep, you guessed it. The whole thing repeats. At this thickness, wave 2 travels an extra full wavelength. That puts it right back where it started, which means it's once again perfectly out of phase with the flipped wave 1. They cancel out. And for that specific color, we see darkness again. So, those amazing swirling colors on a bubble? It's just different thicknesses all over the film, turning different colors of light on and off.
So this is a totally beautiful thing that happens in nature, for sure. But it's not just for show. Engineers have figured out how to take this exact same physics and use it to solve a really common problem.
So what's the use case here? It turns out that if you can perfectly control this thin film interference, you can make things disappear. Or, to be more specific, you can make reflections disappear.
Think about the anti-reflective coating on your eyeglasses or a camera lens. First, they applied this super thin coating. Now here's the genius part. They pick a material so you get two hard reflections, one when light hits the coating and another when the coating hits the glass. That means both reflected waves get flipped 180 degrees. Then, they make that coating exactly 1/4 of a wavelength thick, and just like we saw before, this adds that extra half wavelength journey for the second wave. The result? The two flipped waves are now perfectly out of phase, and they completely cancel each other out. The reflection just vanishes. It's brilliant.
And this isn't just my interpretation. This is straight from the source. The Boston University Physics Department puts it very plainly. The cancellation of reflected light waves is utilized to make non-reflective coatings. It's intentional, precision-engineered physics at work every time you look through a good camera lens. So now, the next time you see a soap bubble floating by, you'll know. Its beauty doesn't come from a color, it comes from its thickness, perfectly tuned to the wavelength of light. You know the secret of the shimmer. So the question is, what other everyday magic is just hiding out there in plain sight, waiting for us to figure it out?